our sets of numbers. They all fall under real numbers for right now. We will get to imaginary numbers later, but they all fall under real numbers. Under real numbers, you have two main sets. Okay, rational numbers, that is anything that can be written as a fraction. If you can put it in fraction form, it is a rational number. If it is in fraction form, then as a decimal, it will either be terminating or repeating. 1/4, that's a terminating decimal, 0.25. 1/3, that is a repeating decimal, 0.3 repeating. Okay? So a rational number can be written as a fraction, and if it was in decimal form, it is repeating or terminating. The other major group is irrational. These are non-repeating, non-terminating decimals. Your square roots that don't have perfect roots, square root of 5. That is going to be 2 point something forever. It is non-repeating, non-terminating decimal. Pi, that's our favorite little non-repeating, non-terminating decimal. Okay? 3.14 is how we round it, but it goes on infinitely non-repeating, non-terminating. That is irrational. Every other type falls under rational. So if you go down that line, your next largest group is integers. Integers does not include decimals and fractions. It includes whole numbers and their opposites. So if you were to put it on a number line from negative infinity to positive infinity, it is the dashes, the -4, the -3, the -2, the -1, 0, 1, 2, 3. It's not the numbers in between. Okay? The numbers in between are rational numbers. Okay? So it is your whole numbers and their opposites pretty much is what integers are. It includes negative numbers. Underneath that, you have just the whole numbers. You'll notice the difference is it doesn't have negatives. 0, 1, 2, 3, 4. Natural numbers is the smallest of them. These are your counting numbers. So when you were in K4 and you had 12 things in front of you and they ask how many, 1, 2, 3, 4, 5. You didn't start with 0 typically. You're counting numbers that don't include 0. All right? So this is the number sets. These are the number sets that you're going to have to know right now. They did it the other way too. You can see it the other way. All of your natural numbers fall into your whole numbers. All of your whole numbers fall into your integers. All of your integers fall into your rational. And your rational and irrational make up the box that is real numbers. Okay? Questions? Let's see these examples. Oh, that's not what I want you to look at. I told you rationals and irrational, terminates or repeats, does not terminate. And then they give you examples there. So example 1 says state the most specific. Not all that it falls into, but the most specific. So if we look at -2, the most specific. So if you're going up the chart, the first one you come to that it can fit into, what do you think it's going to be for -2? That is the most specific. Now, technically, he falls into other categories, right? He's an integer. He's also rational, and he's also real. But the most specific is integer. What about 7/11? You can just call it out.
Rational.
Rational, right? It's written as a fraction. If we can write it as a fraction, it's a rational number. He's also a real number, but he's rational. 2.3, and then we have this little line above it. What does the line above it mean?
Repeat.
Yeah, it repeats, and it's rational, right? And then we have square root of 3. Irrational, right? Irrational. Oh, and I put integer here, and this is a z. Hang on, see what I'm doing? This guy's a z. This is their q prime or whatever they say, irrational. Or, again, if you want to do q prime, I don't care. All right? I'm assuming all of you know how to use a number line, so we're not going to actually make you put things on number lines at this point. But really, everything can be represented on a number line. So you think about, you've been using these forever. You used them when you learned to count. You use them when you learn to add, subtract positive and negative numbers, right? We use it for temperature. I don't know how many people actually have a thermometer that looks like that. Maybe your outside thermometers are still yeah, probably. But your outside ones actually still do that. They're not usually digital, but most of our thermometers that we take temperatures with are digital. Not that they're very accurate sometimes. They'll give you like 7 different readings, but a thermometer is another way to think of a number line. It's just a number line of temperatures, right? I think of like a football field. It's just a big number line, right? I mean, that's all it is. Your positive and negatives aren't really marked because it's more of a distance, but it's the same thing. So if you graph it, you should be able to find it somewhere on the number line. Even your irrational numbers are there. So if I'm graphing the square root of 5, I don't know the square root of 5. It's irrational. I couldn't call it off to you. But I do know the square root of 4, which is 2. And I know the closest square after that is 9, which is 3, square root of 9. So somewhere in between 2 and 3, I'm going to have the square root of 5, even if I don't know exactly where it is, right? So somewhere on the number line, you can put any real number. It is the real number line, all right? And it's represented by a capital letter, and you just put it where it is. If it is a fraction or a decimal, you put it in between. If it is an irrational number, you put it in between the two rationals that you can get closest to. All right, let's look at properties. All right, properties. There's a little bit of memorization that goes along with these, so take note. We have done them many times in the past, though. Commutative property talks about order. Now pay attention, this is addition and multiplication. You see that subtraction and division is not on here for a reason. Commutative property says it doesn't matter what order you added in. 2 plus 3 and 3 plus 2 are going to equal the same thing. 2 times 3 and 3 times 2 are going to equal the same thing. That's what commutative property tells you. The reason subtraction is not on there is because 2 minus 3 does not equal 3 minus 2. 2 divided by 3 does not equal 3 divided by 2. So this only works for addition and multiplication. Associative property. This says that if it's all addition, think of order of operations. You do your parentheses first, right? But if it's all addition, the truth is it doesn't matter where you put parentheses, you're going to get the same answer. If it's all multiplication, the truth is it doesn't matter where you put the parentheses, you're going to get the same answer. That's only if it's all addition or all multiplication. You can change those parentheses around and it will not make a difference. Also not true for subtraction and division. All right? Identity property. If you add 0 to any number, it doesn't change the identity. If you multiply any number by 1, it doesn't change the identity. Inverse, if you add a number and it's inverse, you get 0. If you multiply a number and it's reciprocal, you get 1, assuming that its reciprocal is not 0, that it doesn't equal 0. All right, and then the last one is distributive property, which hopefully you remember because we did it over and over in Algebra 1. If you have a number multiplied by a group, you can distribute that multiplication through to the group. So they have A times the parentheses B plus C. That equals AB plus AC. So all we're going to do is name the property. A, we have 8x plus 5y equals 5y plus 8x. Eber, what is that? Which property?
Is that
commutative? Yep, that's right. Order. They just changed the order and it didn't change the outcome. Lewis, do the next one. 3b times 1 over 3b. That is, yeah, your inverse. If you multiply 3b by its reciprocal, you get 1. C. Let's look at C, Juju. What did they do there? They added 0. What property tells me if I add 0, it doesn't change? Identity. It doesn't change the identity. That's right. D. I'm a little, I don't like how they did D, but that's okay. We'll talk about it. I disagree with them on their answer.
what did you say?
It says associative property. It didn't really change the grouping so much. Oh, I see what they did. Yeah, so they just didn't show it. Okay. So they did the 5 times 2 times pi. There we go. That would have been easier if they had done that. Associative property. I wasn't going to call anybody to do that one. All right, let's look at the next one. Caroline, what did they do on E? Negative 3x times that group equals negative 6x squared plus 3xy. It does have a group in it, but what did they actually do to that negative 3x? Negative 3x times 2x, negative 3x times negative y. What did they actually do here? Yeah, so they distribute it. Does that make sense? Right? So the associative has that grouping, which is actually what they did here, which doesn't show it as well. What they did, though, is they actually gave the answer if you were to actually go ahead and do the multiplication. So that's the difference between what it looks like for associative and what it looks like for something like distribution. For distribution, you're going to have a plus minus in between it. For associative, it's going to be all the same function. It's going to be all multiplication or all addition, right? All right. Any questions on knowing these properties and being able to name them? All right. So you should be able to either name them or give me an example of one. If I were to list them, you should be able to hand me an example. Or if I were to give you one, you should be able to tell me what it is. All right, let's look at some definitions here, or this definition rather. A set is closed under an operation if the result of performing that operation on members of the set always results in a member of the set. What does all of that mean? It means if I were to add or subtract, then will I stay in the same set of numbers? Will I stay in the same set of numbers? So let's talk about this. Addition. If I add two numbers, will I stay in the same set that I started in? By set, I mean natural, whole, integer, rational, real. So if I add two natural numbers, will I get a natural number?
Yes.
And if your answer is no, you're going to have to give me an example for all of these, by the way. Yes, you will. Addition is closed. If I add a -5 and a -2, those are both integers. I will get a -7, which is also an integer. That is closed. If it had popped me into something else, it would not be a closed function. All right? So it would not be closed. So it is closed for addition. We know specifically for addition that is closed. That function creates a closed operation. What about subtraction? Is this closed? If I subtract two numbers in one set, will I always get a number in that set? And if not, give me an example.
No.
So subtraction is not closed. What about multiplication? Is it closed? Yes or no? Yes, it is closed. If you multiply two negative numbers, you get a positive, but positive numbers are part of integers, right? If you multiply two fractions, you could potentially get a whole number, but whole numbers fall into your rational numbers anyway. So, multiplication is closed. So then what do you think about division? No, it's not, right? I can definitely divide two whole numbers and get a rational number, get a fraction, right?
Yeah.
1 is a whole number, 2 is a whole number. 1 divided by 2 is not a whole number, right? Any questions on that? Now, they specifically gave me a set of numbers. They said -1, 0, and 1. Are these closed? And when they gave me this example, I could say, possibly, possibly not. But what they're asking, is it closed in that set? Not in the sets of numbers, in that set. Well, I have -1 plus 0 is -1. -1 plus 1 is 0. That's closed, right? Like I ended up with the same thing for addition. But what about multiplication?
You still will get.
Is it closed? Yeah, multiplication is closed here. Can I give an example of addition or multiplication where it's not closed? What if I add 1 and 1? What do I get? 2. Is 2 in that set? No, it is not. 2 is not in that set. So you have to make sure that if you're saying yes, it is, that you haven't thought of a counter example. And that is a word from our favorite subject, geometry, right? A counter example. So if you use the word always with me, you can ask my child, and I'm going to say, always? Is that really what you mean, right? Because I'm about to provide you with an example of not always, okay? All right, let's go over these. The most specific subset of real numbers to which each number belongs. 3, the most specific one for 3. One smaller. Natural numbers, right? 1, 2, 3.
Yeah.
Whole includes 0, right? So basically whole and natural are the exact same set, but whole has 0 thrown in there. What about -7, the most specific?
Integer.
Yeah, this is an integer. And what about this guy? Rational. It is repeating, all right? Now, when the difference between those 3 questions and the next 2 is it says the subsets, meaning they want you to list all of them to which it belongs. Here is just a real clue if I were to ask this. They're all real numbers, so don't leave him out, okay? So if I look at 0, we start at the most specific, and then it's everything above it. So the most specific would be a whole, and then you're going to go up integer. It's also rational, and it's also real. That's the best way to think about all the sets that it's in. Get to the most specific, and then just go up from there, all right? -18.2. Well, the most specific that is what? Rational. And so if it's rational, it's also right above it. It's also real. Okay? These next one are just naming the properties. I have 3 plus 7 and 7 plus 3. We just changed the order. That is the commutative property of addition. Okay, of addition. Negative 5x plus 0 equals negative 5x. Additive identity property, or you could say identity property of addition, right? Negative 1/2 x times 2x minus 8 is the same thing as negative x squared plus 4x. They just distributed that distributive property. And then negative 18b times 1, anything times 1 does not change the identity. So this is, they have multiplicative identity or identity property of multiplication, either one.